Oh, I did want to show you guys before we got started here. Wait. I posted this poster on your Moodle page. This isn't your Moodle page, but it's okay. So have you guys heard about Camp OC? They run it here. Anyways, they're hiring students. So I don't know, do you guys go to school in the summer? How does your program work?
We are not required. You can.
Yeah. Anyways, it's Monday to Fridays, kind of 8 to 4. Probably not that applicable in terms of like your resume for you guys, but probably a pretty fun job, and it's here at the campus. So anyway, and they're hiring. Yeah, during the summer. And worst case, well, they're having info sessions today from 11 to 12. Is that right after? Yeah. And there's pizza and refreshments. So, and then there's another one at 5 to 6. So I don't know what the pay is. I'm assuming they'll tell you what that is if you go. But anyways, so they're hiring students, but also free pizza. So why not, right? Yeah. Oh, here it is. How fun is that? The 68, 95, 99.7 rule. I know. Don't we wish we were there instead? Sounds nice.
The thing is, when you learn that, you will believe that you can put it anywhere, but you can't use it anywhere. Everything is not normally distributed.
I know. Well, a lot of things are normally distributed, but for you guys in data science, no, it's not going to be normally distributed. It's like, oh, crap. Now what do I do? Yeah. But for you guys, there's lots of other distributions. We don't really get to talk about any of them, which is good because it's been a long time for me.
There's another stats.
I don't know. I don't know who's teaching that one. I have no idea. I don't know if Claude will be back. I have no idea what's going on. But they did change so that I am the instructor for this course. So even if he does come back, then I think you're stuck with me. So thank you. I know. Yeah, just like yeah, you guys get changed all around. Okay. Oh, I put them here, didn't I? Okay, so we're still talking about ANOVA, and I was all proud of myself. I said, hey, I scheduled 3 days for chapter 5. There's no way I'm gonna need 3 days. I might need 3 days. So anyways, so if that's the case, then I'll push the due date for the lab, of course, and you'll have time to work on it. But so anyways, let's do a little bit of review. But you have it there, right? So we ended on saying that for ANOVA, we either test that H0, and this is kind of where we start off and we say, well, we're just going to compare the means of all these groups. Is there one that is different? Right, and so we can say that mu1 equals mu2 equals all the way up to mu3, et cetera, right? Are they all equal to each other? And then the alternative hypothesis is that some mu I does not equal mu j. So one of these is not like the others. Doesn't tell us which one or anything like that. Right? It just tells us there's something that you can look into here. Or we can use the one-way ANOVA model, which says that y is mu, so the overall mean, and then so we strip that overall mean away, and then we just talk about the difference from the overall mean to each of the effects, right? And so mu plus alpha I plus that error term, where the alpha is the treatment effect. The treatment effect in group I. So then what we can do, we said, and this is where we kind of finished last day, we said that we could rephrase our null hypothesis in terms of just the treatment effects, right? Are the treatment effects 0? So is alpha 1 equal to alpha 2 equal to all the way up to, oops, 0? Are they all equal to 0, meaning there's no treatment effect in any of these groups? Or the alternative hypothesis is that some alpha I does not equal 0. So that's kind of where we ended, right? We use the f-test. The ANOVA gives us an f-test and a p-value. And so running the ANOVA, and I guess this is the end of our review, so I'll put a little squiggly thing. Running the ANOVA gives a p-value, okay? And a small p-value, of course, tells us that there is something going on here, right? There is some treatment effect in some of these groups, in at least one of these groups, right? So it gives a p-value, and a small p-value tells us there is a treatment effect in at least one of the groups. There is a treatment effect in at least one of the groups. You might have guessed that that's not really sufficient to publish a report and say, yep, there's a treatment effect there. The end. Right? You can't say that. So then we need to go a little bit deeper. And we have some options there, right? We could do kind of pairwise T-tests, right? Break it down, look at all the different pairings that we could have and do T-tests among them, right, for the means. Or what we can do is we can look at confidence intervals for each of the means in each of the treatment groups, right? And then we can compare confidence intervals. We can even do things like find a confidence interval for the difference between the means in two groups, right? And so, yeah.
I was just wondering, we used to do the one-way ANOVA. We just run it and we alpha less than 0.05.
Yeah.
But what we have is say we have a control and a treatment.
Yeah.
Right?
Yeah.
And if we run a one-way ANOVA and we have a p-value of less than 0.05, we conclude that the treatment has an effect.
Yeah.
That's what our.
That's right.
So,
So how is that different from a t-test?
yeah,
It's not. But the problem is because what you're thinking about is just two groups, right?
yeah,
So if you have two groups, it's no different. It'll be the same, right? But the ANOVA can handle multiple groups, right? And so, and that's when we start using it. So if you're only looking at a control versus a treatment group, I would say you're better off just using a t-test, right? Because the ANOVA is going to give you the same thing, but it gets confusing to think about an ANOVA in that way. So I would say ANOVAs should only be used for more than two groups. Right? But yeah, otherwise, you're right, they're the same. It's good. So if, and I'll do all caps here, screaming, if the p-value is small, right, then we want to know, well, what is the difference, right? What is the treatment effect that is different from the others, right? We want to dive in there and figure out which treatment actually worked, or, you know, whatever the scenario. We use treatment pretty generally. Okay. So if the p-value is small, we want to know what the difference is, right? We want to know what the difference is. And I'll put in brackets which treatment or treatments is different. So of course, just like we've said before, right, the ANOVA is kind of the gatekeeper. If your ANOVA is not significant, you're not going to dive in and have a deeper look, right? You're just going to say, hey, there's nothing going on here. Shut it down, right? So your first step is going to be check your ANOVA, make sure it's significant. Then we can look at the individual groups that we're looking at, and we can do things like build a confidence interval on each of these groups, right? How big of a margin of error do I have on these estimates, right? Are my estimates going to be really good, right? Making my margin of error really small, right? Or is it kind of big and I can't really tell much from my data, right? And so put it on a new page, I think. To determine what the difference is, right, we're going to build confidence intervals. We've got a couple of options, right? Main ones being on each individual mean for the groups, right? We've got, say, 4 groups, right? Each of them has a mean, and I build confidence intervals around those means. Or the other option is, if I want to compare 2 groups specifically, then I can do a confidence interval for the difference of those 2 means. So to determine what the difference is, kind of between groups, I guess I should add. What the difference is between groups. We can build confidence intervals which from now on I'll just probably just write CI, confidential informant. No, I watch too many police shows, I think. Like confidential, I'm like CI, confidential informant. DB, dead body. I love those stupid shows. Anyways, that doesn't matter. I'll make it a bonus question. What kind of TV does Emily watch? Drugs Inc. mostly. No. All right. So for individual means, we take, of course, our estimate from our sample, our yi bar. We're going to have a y1 bar, y2 bar, y3 bar, y4 bar if we're assuming we have 4 different groups, right? And so, and then plus minus t star times the standard deviation, which I'll talk about, over, or times the square root of 1 over n I. Oh, I can't talk at all today. It's bad news for you guys when you show up to listen. So we need to talk about a couple of things, right? So where t star is from the error degrees of freedom, right? And whatever confidence level you want, 95% typically is our go-to. And our confidence level, of course. Oops. So T star is same as always. It's just that it's from the error degrees of freedom. So you've got your, you've already run your ANOVA, right? So you've got your ANOVA table, and so you know your error degrees of freedom, and that's what you're going to use to find your T star. And so that's the only hang up. Yeah, that's right. And it is too. Yeah. The n will could change per group. Often we have balanced designs, especially if we're looking at experiments. So then the n's will all be the same. But if we're looking at observational data, then potentially these n's will be different. And so we need to account for that. But the standard deviation and the SD is going to be the square root of the mean squared error, also from the F table. That's the standard deviation that we're going to use throughout. So it's going to be just the square root of the mean squared error. So it'll always be the same regardless of if we're comparing one group or looking at one group or comparing 2 groups, right? It'll always just be the square root of the mean squared error. So that's nice, right? We can find our degrees of freedom from the table that we've already got and our standard deviation from the table that we've already got. And then we just kind of plug them in, see what we get. Or we can build a confidence interval for the difference in 2 means. For the difference in 2 means, mu1 minus mu2, for example. By doing y1 bar minus y2 bar, put those in brackets just to show that that's going to be one thing, right? One estimate of the difference. Plus minus t star, again, same t star as before, same standard deviation, and then except now I've got 1 over n1 plus 1 over n2. And potentially allowing for 2 different sample sets. So I would do the individual confidence interval. I would do it if I'm just looking at them overall, right? If I just want to compare them, I would probably build confidence intervals for each of the groups, and then just look for kind of overlap. If they contain a certain value that I'm looking for, maybe I'll do that. But most often we want to compare groups, and so that's when we use this, the difference in the two means. So answer it, sort of? No?
So, let me align in my mind. So, if you start with individual means,
Yep.
right, you have a CI for each group.
Yep.
Then you would see there each one is somewhat of the same band,
Mm-hmm.
and you would see one that is, let's say, separating.
Yep,
So that one could be the significant factor,
exactly.
significant group.
Yeah.
Right?
Mhm.
Then for this one, mu1 always the control, or
No, it's just any group that you want to compare to another group. So I'm just saying group 1, group 2
and
arbitrarily.
you would be concluding if they are the same or different.
So we're building a confidence interval for the difference,
Yeah.
right? And so usually how we end up using it is if the confidence interval for the difference contains 0,
Yeah.
then there's no reason to say that these two things are different, right?
Okay.
So if it spans 0, then no, these two groups are the same. If the whole interval is positive, for example, then there is a difference here, right? And more specifically, mu1 is consistently higher than mu2 to get a positive value. Whereas if you're on the negative end, right, then mu1 is consistently less than mu2 to get that negative value. Right? So, and that's what makes the two means more useful, I would say, right? The single confidence intervals, like you said, give you kind of an idea of any sort of overlap,
Yeah.
right? Because what you have for the individual means might be something like, let's say our group 1, 2, 3, 4. Let's say our means are here. Just as a kind of a rough estimate. If my confidence intervals go from here to here, right, and my margin of errors are super huge, maybe it tops out there. That's not going to be very telling, right? There's a lot of overlap. Even like this guy here would be cut off a little bit, right? So here, this would be a large margin of error. Whereas if you had a small margin of error, right, something like this, right, then, like you said, now there is a difference, right? There's even a difference between group 1 and group 2 and group 3, but also all of them to group 4, right? So now there's a lot more differences. And so that's how we would use the individual confidence intervals. But I would say more often we would use the comparisons. Right? And so here I'll just make a note that these are small margin of errors. And that all hinges on the overall standard deviation, the square root of the mean squared error. We use the confidence intervals for the difference in two means we use the CI for a difference, oops, in two means, oops, to determine if they're different. To determine if they are different. Specifically, did you guys end up using confidence intervals for hypothesis testing? Or did you just use p-values? Probably just p-values, yeah.
Last
term, yeah.
It's
All p-values. So, but I don't think that you'll be that surprised to know that you could just as easily use a confidence interval instead of p-values, right? Because if I'm able to say that I'm 95% confident that the true mean is somewhere in this realm, right? That's the same as saying I'm 5%, I'm willing to be 5% kind of, yeah, not confident in my results, right? That's the alpha equals 0.05, right? So, so confidence intervals and p-values, they're the inverse, I guess you could think of them as, right? And so a 95% confidence interval is the same as a two-sided 0.05 alpha level, right? So, we can use confidence intervals to test hypotheses rather than p-values. In fact, there's kind of a push towards kind of not using so many p-values, right? We use them because we're used to them and we like them, right? But we should kind of be migrating more towards using confidence intervals instead, right? Because not only does it tell us that there is a difference, right? It quantifies the difference as well. And so it does two things at once. And so we can use confidence intervals to test hypotheses rather than p-values because two group means are significantly different right? That makes it a two-sided test or a two-tailed test, right? If they're just different. So it does only, well, I mean, you could adjust your confidence interval if you want a one-sided test, but usually the default is a two-sided test, right? Unless it specifies. So this makes it a two-sided test. If and only if, oh, I did it. I said I'm gonna write it out, but you guys probably know IFF, if and only if. Anyways, if and only if oh, I blubbed it. Well, actually, I just need to insert at the 5% level. So I'll keep that hanging around here at the 5% level, because that's what I said. If and only if the 95% confidence interval for their difference does not include 0. So if it includes 0, then the difference between the two can be nothing, making them the same, and so then you would not be able to reject your null hypothesis. And if it doesn't include 0, so it's consistently positive or consistently negative, right, then that's proof that you can reject your null hypothesis without hinging it on p-values. So like we said here, these confidence intervals, which we saw here, these confidence intervals tell us how well we're able to estimate these parameters, right? We're trying to estimate, so this line here, this is our sample mean, right? But we're trying to use this to estimate our population mean for group 1, right? Estimating our population mean for group 2, right? We're always using our statistics, our sample statistics, our sample estimates to try to estimate the population parameters. Right? Yes.
So what if the confidence interval
Yeah.
drop?
Yeah. Yeah.
So what if the
Oh, here.
CI is like this? I mean, it will include
Well, so
0.
here, yeah, so what I would do,
So let's make it marginal. So yeah, if you calculate for that, it will include 0, right? But it will.
well, not necessarily, because these are the individual confidence intervals, right?
Yes.
Right? And so what we would have to do is we would have to take this minus this, and then account for the spread that we would expect to see with this many sample size, or this sample size and this sample size, right? And so it's not necessarily going to translate to this, right? This minus this. It'll be its own interval, right? Because this minus this, the estimate would be somewhere in between, right?
Yeah.
But the bounds might go somewhere like this, or might even be shorter,
Yeah.
right? It just depends on, so that's why you have to do it for the difference. So it's going to be hard to tell just by looking at the individual ones. Here we can look at the individual ones and get some idea of what's happening. But then, and especially if we've got like 15 groups, right? It helps us identify, okay, which ones am I going to look at first, right? And then, but then you'll want to look at the differences, the pairwise differences.
You have many pairwise.
15 choose 2. Ouch, a lot. Good thing we've got software, right? So, yeah, not fun. But usually, would we want to have, especially an experiment with that many groups? Probably not, right? You would probably want to kind of boil it down to the bare minimum, right? Because there's going to be, at 15 groups, I don't really care what you're measuring, there's not going to be clear distinction between every single group that you're looking at, right? You should probably be able to group them a little bit, but it just, I guess it depends on the scenario. I've never seen something where you've had to have that many groups. But what do I know?
Just to close this
Mhm.
issue. So let's say, for example, you have a difference in these with the confidence interval of, let's say, -1 to 15,
Yeah.
positive 15. So it means that their difference, and it includes 0, right? But most of the time it is positive.
About, yeah.
So you would still conclude that there is no difference.
Yes. Because I'm still 95% confident that it's somewhere in there. And so I wouldn't want to contradict myself and say, so there could be a difference a portion of the time, right? That one is a little bit tricky though, right? It's kind of you could play around with, you know, changing your confidence level. And what else could you, that's probably your only option, right? Yeah, changing your confidence level, you know, is 0 still in there at 90%, right? How far does it go at 99%? Right, that kind of thing. You'd want to play around with it a little bit because, like you said, it's like, well, it's close, right? And I would probably use that as an argument, you know, to do a 90% confidence interval and see, you know, if it's not included in a 90% confidence interval, well, should we be basing our results off that, right? But you don't want to argue for significant results when the data is telling you, no, there's none, right? But yeah, it's just things to, and it depends on the scenario too, right? We're not really talking about any specific data here, so it's hard to think about, well, what are the differences, for example, right? But yeah, just kind of have to play around with it. Yeah. Okay, am I ready to go into effect sizes here? Did you guys talk about effect sizes last term? Or is this the first time you're hearing that? Could be the first time, could very likely be the first time. Yep. Okay, so we've talked about p-values. P-values tell you if something's going on. Confidence intervals tell you, you know, what your estimate or how precise your estimate might be, right? How much money should you be betting on this estimate, right? And then the effect size tells us, well, compared to everything that's going on, does this size of the effect really matter, right? And so, you know, what's an example, right? If you're finding that there's, you're working in a hospital, for example, you're analyzing their data. And so you're analyzing and you find that, the difference in wait times at the hospitals. Did you leave your phone there? Yeah. We assumed someone was coming back for that. Yeah. We were gonna bring it to the library after class if you didn't come back.
Yeah, thank you. Yeah.
Hey, that's not your graphing calculator, is it?
No.
Okay. That was your chance. I love those graphing calculators. So nice. I know they're old, but I just love mine. Oh yeah, so the effect size, so the waiting times got completely sidetracked. Oh, you've done all this research and you figured out, okay, there's a significant difference in wait times. I can't think of a reasonable scenario here. And then they say, okay, well, what's the difference in the wait times? Oh, it's between 1 and 2 minutes. It's significant though. And everyone's kind of like, why would we care about 1 or 2 minutes, right? Bring me 15 minutes, 20 minutes, then I'll think about it, right? But 1 or 2 minutes, who cares, right? It might be significant, and you might have gotten that far to say, oh no, there's a significant difference here. But then when it really comes down to it, do we really care about this difference that we're finding? And that's what the effect size is meant to help out with, is because the effect size takes into account the spread in our overall data, right? And says, well, a 1 minute difference, right, compared to how this data is behaving is not going to make a huge difference. Shouldn't use difference. It's going to be, it's not going to change anything, right? And so confidence intervals, CIs, tell us how well we can estimate theoretical parameters. Oops. Theoretical parameters, right? That's our mu I. But it can't tell us, that's, sorry. I wrote it down because I wanted it to be good, and then I keep jumping around on the lines. That's me reversing. Should use my finger here. But to determine if the difference, or if the differences we have detected which was through our F-test, right? So we detected some differences using the F-test, and estimated that's through our confidence intervals. Matter in actual practice. Matter in actual practice. So, but to determine if the differences we've detected and estimated matter in actual practice, we need to find the effect size. We need to find the effect size. So the effect size for a single group, effect size DI, capital D is the effect size. Which is going to be alpha I hat. That's the predicted, or the treatment effect, the estimated treatment effect. estimated treatment effect divided by the standard deviation, right? How much spread am I looking at overall? This is the same as yi bar minus y bar divided by the standard deviation, right? Where the standard deviation is still the square root of the mean squared error. And I'll scoot this down one. Square root of the mean squared error. So this is the group mean. This is the overall mean. And that is just the treatment effect, right? Yes. Well, the residuals are going to be from each individual group mean to observed points. So this is one step higher than that. Because you go from your observed y's to your group mean to your overall mean. Right? And so the residuals are from the observed y's to the group means. And then here we're talking about the treatment effect is from your group mean to the overall mean. If you want to think about it that way. So we can also calculate the effect size. The effect size of a difference between two groups. Difference between any pair of groups. You can drop the subscripts, right? Often it'll be clear from the context, and we just often just use capital D for the effect size. And it's called Cohen's D, I think. I don't know, the guy who made it up. So the I and the J are just indicating the two groups that they're coming from, right? And so then you've got yi bar minus yj bar divided by the standard deviation. And again, that standard deviation is the square root of the mean squared error. So we usually want to have some cutoffs, right? What are these effect sizes? How can I determine if there's a large effect size, which is usually what I want, right? I want to show that, hey, this is actually having a big effect. This treatment has a big effect on the outcome. Whereas a small effect size, nah, we don't really care about that in practice, right? And so we typically want a large effect size since that means that the treatment effect large enough to matter, since that will mean the treatment effect
will be large enough to matter. So some cutoffs, and I've seen a couple floating around, but because it's Cohen's D, I'm going to use Cohen's cutoff. And so in general, we say that a small effect size is anything less than 0.2. Right. A medium effect size is up to 0.5. Anything larger than 0.8 is large. And then we can go a little bit further and say, well, very large, oops. Very large is something like 1.2, and there was even a huge on there, which I thought was pretty fun. That 2. Right. So an effect size of 2 would just be massive and honestly kind of unheard of. So just your effect size through the roof, and I guess it can happen, but usually we're looking at things, 0.75, 0.89, really good, right? And so the textbook actually doesn't outline any cutoffs. They want you to think of it as percentages, right? And so this would translate to a large effect size would be anything where it's 80% or higher, right? Medium 50% or higher. But I actually like to have just kind of some sort of setup where we can say, okay, because it's less than this or larger than this, we have a large effect size, for example. Yeah. So the effect size just to summarize kind of what it's doing, right? It tells us how large is the group to group variation, or how large is the group to group difference, sorry. Well, I guess it's the same. Compared with ordinary unit to unit variation. Compared with ordinary unit to unit variation. Because we're looking at, let's talk about the 2 groups that we're comparing, right? We're talking about how does the mean of this, so the difference between these 2 means, how does it compare to the standard deviation of the overall data set, right? The spread in the entire data set, right? That's our standard deviation, the square root of the mean squared error. And so how large does this difference compare to the standard deviation, which kind of brings us back to where it all probably began. Did you get Z scores, right? We're talking about how far is this X from this mu when I take into account the standard deviation, right? We're talking about the same thing here, right? I'm talking about a difference divided by the standard deviation, right? How big is that difference between these 2 groups if I take into account the spread that I'm expecting to see, right? And so that's what the effect size does. All right. That's all I prepared for today. I thought that was going to take me way longer. So now, well, I can keep going, but I'm going to need next day anyways. So, and do you guys have a test after this? Yeah. So how about we call it a day? Yeah. Is that okay? Okay. Good. Yeah. Just take a moment. You can use the room. You can have a nap. You can stare out the window. Do whatever you need to do to get into that groove. Yeah, sorry, I should have prepared more, but I was like, that's way too much to talk about in one class. Way too much.
Yeah. My question is, so the first unit we did regression, we want to predict how we want to build a model